there'll be a way to orient the knots so that the rope of the band is oriented, so it's compatible.
I mean, twisting twice obviously has no effect.
Yeah, I mean, because essentially all you're getting is, you're attaching a band to essentially to something that's contained in the ball. So you can just untwist whatever's in there. I mean, it's really like a light bulb kind of thing going on. You've got sort of one fixed up there, and you want to switch through that you can just isotope things around to make the band look standard. And that includes isotoping out any twists. Are we good, Dave? Okay. All right, so in my notes, we're starting part 3. I don't think we're in part 2, but it tells me that it's called bridge splits. Okay. All right, so the main object of study here and for much of the rest of the class, in fact, will be the notion of a trivial tangle. So what is a tangle? A tangle is a pair B, and then I'll use like a script T for the tangle, for the T part, such that B is diffeomorphic to B3, and T inside B is a properly embedded one manifold. Okay. So this is just a relative notion of basically a knot or a link. So BT is called trivial, or a trivial B tangle would be another word I might use. Trivial or trivial B tangle. To be a little bit more precise. If T has no closed components, sorry about that. New chunk and making this and T is ambient isotopic, real boundary, relative to the boundary. Sorry, I should say, this is rel boundary of T. This isotopic. T is ambient isotopic into the boundary of B relative to the boundary of T. Okay, so in other words, we can take the strands T and we can isotope them to lie in the boundary of the ball. And this can be done without moving the endpoint of the strands. Okay. So just to set up some notation, we're going to write a tangle as, okay, this is a moment of truth. Do I dare change notation? Well, let's do it like this. So T1, T2, all the way up to TP. I guess I didn't say in the definition what I mean by a B tangle. So a tangle is a trivial B tangle if it has no closed components and B properly components with boundary and its isotopic in the boundary. So we'll write the tangle as the union of these components, and we'll call these the strands. We'll call the T sub J strands. J equals 1. Okay. And then I guess the last thing I should say is the equivalent, what is the equivalence class of these things that we consider? We consider BT up to ambient isotopy, rel boundary, or equivalently, up to diffeomorphism of boundary. Diffeomorphism of pairs. Okay, so all right, let's draw some pictures of examples. Okay, so the first example I'll give is we could have BT just being the product of a disk D, and then a subset, which I'll denote by XB, which is just B marked points, and then crossing with the interval I. Okay, so what does this look like? Maybe just to be clear, this will be the pair D2 XB, where we have B points inside the two disks. Okay, and we cross with I. Crossing the two disks with I gives us a 3-ball. And crossing the strands, or the points with I, gives us properly embedded 1 manifold. And so then that's T living inside of. Okay, so that's a typical example of one way we can think about a trivial tangle. Does anyone have any questions now that I've given the definition and drawn an example?
The meaning of property.
Oh yeah, good. So a proper embedding means that the boundary of the thing you're embedding is taken into the boundary of the thing you're embedding it into. So for example, if I'm in a 3-ball here, let's draw some properly embedded objects. So the first sort of thing that can be properly embedded would be as if we just have a closed one manifold. So embedding from a closed one manifold into a manifold will be a proper embedding as long as it's disjoint from the boundary. So a properly embedded guy would need to have its endpoints on the boundary sphere. So an example of a thing that wouldn't be proper would be like if I took it's a little hard to tell that it's actually in there. But if I just put an arc, a compact one manifold of boundary completely in the interior.
What do you mean by B is equal to B?
Diffeomorphic? Yeah. Or homeomorphic. Basically, it's a copy of the 3-ball. I guess I could have just written it's a pair B3T.
So is all these sets located in like R3?
Yeah, we'll usually think of them as a subset of R3, but when we start gluing these things together, it will be useful to think of them as different copies of the same manifold. So it's just, I don't think there's too much of a problem there. Does that answer your question? It's just a 3-ball. Okay, good. Any other questions? Okay. So I guess my second example would be, oh yeah, so we could take BT to be what we get if we take a knot in S3 and we puncture it. So we remove a neighborhood of a point which lies on the knot. Okay. And so sometimes in this case we would sometimes write this as maybe B3, and then sometimes I'll put a little circle above the thing to notate that it's been punctured. So what does this look like? Well, if we remove a neighborhood of a point from S3, we're left with the 3 ball. And since that point was located on a knot, we get a, I wanted to draw, anyway. Of course. We get a knotted arc in the 3 ball. And this one is not trivial. Okay, and the reason it's not trivial is because there's no way to isotope that arc into the boundary of the 3 ball. If there were, then because the thing we removed, on the outside here, in order to get back to the original knot, we just removed a small ball located on the knot. So that means we removed this trivial ball arc pair. If this were isotopic on the boundary, then the original knot would have been knotted. Okay, so one way to think about trivial tangles is that the arcs can't be knotted or with themselves. Okay. And then maybe I'll draw one more picture just to sort of establish a convention of one way to view these things. So, okay. So this is an example of a trivial 3 tangle. Okay, and so in this view, we sort of think of the 3 ball as sitting above the half plane, and we think of the boundary of the 3 ball down here as being the plane. And so in this example, this is sort of a complicated enough example that it's not obvious that this is a trivial tangle, but without too much hard work, you can sort of see that it is. So for one, we can sort of fold this arc down to the boundary like that, right? And then we can take this arc here, and we can sort of fold it down kind of along there, and then it loops around back. And it sort of folds down there. So can you kind of see these membranes that I'm tracing out? And then where would the last one go? Well, I won't draw the membrane in, but it would do something like that, kind of around the back and outside. So this is the hallmark of a trivial tangle. We can push all of the strands down to lie in the mesh. Okay. All right. So another definition. So I'm doing something radical here, which is probably not advised, which is I'm going to give an object a name that people don't normally call it in the literature. I know, it's crazy. I asked Alex what he thought about me doing this, and he didn't respond. So I took that as, that's okay. So a membrane is something that's usually called a bridge disk in the literature. Although in an original paper by Otal, one of the first papers on the subject in French, he called them membranes. The French word is membrane. And I thought that was just much more evocative and fun than bridge disc. So I'll probably use membrane, but every time I'll feel self-conscious about it and say, or
Well, it sounds like you're doing string theory, so that's good.
yeah, right, exactly. Yeah, it's more fun. It's more fun. So a membrane, or a, I think I mentioned over here, these are called strands, right? But I don't remember underlining it. Okay. So a membrane for a bridge disc, a membrane or a bridge disc for a strand T, so a strand T, so just one of these strands in our tangle is a disk delta, which is inside B. Okay. I'm purposefully not saying anything about how it's sort of embedded, such that I guess this disk has a couple of properties. So the first is that such that the intersection, so delta intersects the strands of the tangle precisely in T. And the boundary of delta, sorry about that, can be written as T union T star. Where T star inside the boundary of the B is an embedded arc with T star intersect boundary of the tangle equal to boundary of T. Okay. I think that pins it down. And we'll just say T star. It's an embedded arc, comma, called a shadow. Okay, so for example, here we have our arc T. Maybe this is the third arc of this tangle. And we have this disk delta, maybe I'll call it delta 3. And the disk delta is, I like to call it a semi-disk. I'll add that here. I don't know where I saw this, but in my mind, a semi-disk is like a disk exactly like this, where it's basically a bigone, where half of its boundary is in one place and half is in the other. So it's the semi-disk between the strand and the shadow of the strand, which is an arc in the boundary to a sphere that has the same endpoints as the strand and is disjoint from the other points in the two sphere. Okay. Okay. And then maybe I'll come down here. So a membrane system, I guess this would maybe be called a collection of bridge disks or a system of bridge disks. For a tangle, is a collection of disjoint membranes for the strands of T. So maybe I'll have delta equals delta 1 all up through delta B, where delta J is a membrane for the strand of TJ. So in this picture we have this is a delta. This is delta 2 here, and this is delta 1 in here. We have shadows T star 2 and T star 1. I guess these are T1 and this are T2. So that's a membrane system for that trivial tangle. and then move on. Okay. Does anyone have any questions? Membranes, bridge discs. Okay, so here's a proposition that I think is a good exercise for everybody to work through. So let BT be a tangle. So the following are all equivalent. The following are equivalent. First is that this tangle is trivial. The second is that there is a membrane system for the tangle. I think I'm just going to add another one on the fly because I realize it's a question that usually gets asked. Each strand. This is a little, I guess, this is a little improper since strands were defined for trivial tangles, but anyway. Maybe more broadly, a strand is just a component of a tangle with boundary, a non-closed component of a tangle. Each strand of BT has a membrane. Okay. Hopefully that was right into this. There is a radial Morse function on B, radial Morse function H from B to, I don't know, I guess maybe to R. With a single critical point, such that the restriction to the tangle has a single critical point on each strand. And then the last one is that the pair BT is diffeomorphic to the pair that I described over there, D2, comma, XB cross I. And so this is this diffeomorphism is not necessarily a real boundary diffeomorphism. Right? Otherwise, this would be saying that all trivial, there's only one trivial tangle because we consider trivial tangles up to diffeomorphism pairs real boundary. So if they were all diffeomorphic real boundary, they'd all be the same trivial tangle. They'd all be this one. What's actually true is that there are many different trivial tangles. So for example, real boundary, this one of the dots, it's called ellipses. Without those things, this tangle and this tangle are actually different. I guess given an identification of the boundary, that's important. But maybe the obvious one. But if you allow the diffeomorphism to move the boundary, then you can see that they're the same. Right? I guess equivalently, there's an ambient isotopy straightening out any trivial tangle, provided you can move the points in the boundary. And you can see exactly how that would work, right? I just sort of untangle the tangle by dragging the points around on the boundary. That's an ambient isotope. Okay. Cool. Any questions about that? So various directions of that proof are immediate, but they're all worth thinking about it.
For number 3, is there some innermost disk argument required? I mean, that seems to be the hardest one.
Yeah, that's
If everyone has its own membrane, how do you know they don't crash together?
exactly.
So that-
You're right, that's the hardest one. Okay, good. Yeah, that, basically that 3 implies 2. Although maybe,
Can be avoided if you.
maybe it can be avoided by going
I see.
a long way around.
Yeah.
I don't actually know. Something to think about. Good exercise today. Any other questions?
Sorry, I
Yeah,
have
please, please.
number 4, what is the word right before Morse function?
I wrote radial, I think. This one?
Yeah.
Radial. Yeah, I mean, that's maybe a little non-standard. You know, what I'm thinking here is it's a Morse function that just measures the distance that you are from the center of the
You could
ball.
just say there is a Morse function.
Yeah, that's right. I think in my notes I didn't include the single critical point. For me, probably the adjective radial would mean there's a single critical point at the center. But yeah, Dave's right. Or maybe you would call it a height function. You know, maybe a height function is a Morse function. I don't know. I'm not sure there. But good question, thank you. Am I writing a little crash over there? Any other things I can clarify? Okay. Okay, so here we go. So now we're going to talk about what happens if we have different membrane systems for a given tangle. So a membrane system delta prime for a tangle is called jump equivalent. This is also another term that I don't think has been used this way in the literature, but well, that's not true. I got this from somewhere. I think I got this from an old paper. I'll figure out where I got it from. Anyway, membrane system. I haven't heard people studying trisections talk about this, but I think it'll be useful. Is jump equivalent to another membrane system, say delta, if delta prime becomes isotopic to delta after some number of jumps. Clearly that's what it must mean. Jumps of delta prime over delta. Yeah, I thought I knew all the tricks to make the chalk last week, but not doing very well. Okay, so what is a jump? Okay. So we're going to take membranes delta I and delta J, and I guess we're going to think of these as components of the system delta prime. And we're going to let dj equal the boundary of a regular neighborhood of delta j. Take that boundary, intersect it with the interior of B, and take the closure. So here are some serious points of topology going on right here. So I'll draw a picture to make sense of this. We can map it in a second. Oh, maybe I'll start drawing that picture now. Okay, so what do I have? I have a I have this membrane delta J. Okay, so this is That's way too small. So this is delta J. And what I do is I take a regular neighborhood of this entire semi-disk. So on the boundary, that regular neighborhood looks like a disk neighborhood of the shadow. And then over the top, it sort of looks like a cap. And so in fact, that's sort of key to this construction, is that the regular neighborhood of this thing is a ball. And then what we do is we sort of take the boundary of that ball consists of a disk which is flat in the boundary sphere. And also a disk which looks like sort of a cap over the regular neighborhood, which is properly embedded. Okay, so Dij is properly embedded, so that would be, maybe I'll change colors. So this guy up here, this is Dj, is properly embedded with this. Okay. So next we're going to let B be a band connecting delta I, our first guy, which I didn't draw yet. So let's see, how do I draw it? Yeah, maybe I'll just draw a piece of it. Maybe it just sort of looks like this. So this is our other membrane. That's an I. So the band is going to connect delta I to this cap, to the cap Dj. Okay. And then we're going to let delta I prime be delta I union the band B union the cap D sub J. So let me draw my band in here. Band will be red. It'll look like it comes out front. Let's go back. Oh, it just goes to here. Okay. So see, B just connects this disk, this membrane delta I, to the cap Dj. And then when we perform the jump, what we do is we get rid of this old membrane. This was T sub I. And the new membrane we're going to get is going to, let's draw a master. This is T sub J, and its old membrane, or it still has the same membrane, delta J. But this new one, maybe I'll draw it like a purple. So it follows the old membrane, and then when it gets to the band, it sort of follows the band, and then does something like this. And then if I render this, it just goes back off this way. Let me make sure I get it right.
So that should be the boundary DJ.
The band, which one? Sorry.
The very last delta I prime should be that. Shouldn't that be the boundary DJ? You don't want the whole. You want it to be.
The DJ is the disk.
DJ is already the boundary.
DJ is already a disk. DJ was it's the boundary cap.
Oh, okay.
I didn't give a name to the 3-ball.
Okay.
Right, that was just this.
Oh.
But good question.
So you're jumping delta prime over delta?
No.
Which one is?
No, I'm not. No, good question. I'm doing a jump of one membrane disk of delta prime over another.
So this is internal.
Oh, this is not right. What did I write here? Oh, sorry, thank you, Joe. This is wrong. We don't jump delta prime over delta. We do jumps of delta prime.
It's always hard to write this down because in principle, that whole, from your jumps at every time it's a different memory system.
That's true.
So
Yeah.
every time you do it, you have
Right, yeah.
you change one membrane in your life.
Implicit in this is that we're calling it delta prime again after the jump. But let's make sure we can understand just the elementary step, which is you essentially take this original disk delta I and you sort of move you isotope it over to a neighborhood of another one, and then you bubble it over. Okay. And so you can think of this as a new membrane for the original arc TI. I guess that's maybe something to investigate, why that is a new membrane for it. And so yeah, so then I guess usually what you write then, maybe we should give this new system a name. Okay. All right, so let's do this. This will make it a little bit more clear. We'll let delta double prime equal delta prime minus delta I union delta I prime. So we throw out the old delta I and we have the new delta I. This gives us a new membrane system, and we say that delta prime is obtained from delta prime via a jump of delta I over delta J.
So why aren't you calling them handles like?
Well, they're not really handles.
I'm done with it.
Yeah, so I mean, I don't know, I like things that have different names. But yeah, it's a slide, right? It's a slide of sorts. There are many slides, as we'll see, but it actually gets a little confusing when you're writing up the moves for like bridge splittings or or like in generalized bridge splittings or generalized bridge trisections, where you have handle slides, and then you also have maybe what are called arc slides or jumps, or well, there's really a couple things, and it actually gets a little confusing if you just try to call everything slides of various sorts. So maybe this is overly careful, but I guess this is I don't know. I don't want to go ahead anything there. Okay. So yeah, maybe I guess I mentioned that maybe an exercise is to check that delta prime is a membrane system for B2. Yeah, so actually, I guess a better way to exposit this would be to have defined a jump first, and then to say that two membrane systems are jump equivalent if they're related by a sequence of jumps. That would make it a little bit clearer. Note to self. Okay, any questions? Okay, this is pretty good. So I'm going to state an important proposition here. If delta and delta prime are membrane systems, for, I guess, a fixed angle, BT. Let's write it down. A fixed angle. Then delta and delta prime are jump equivalent. And there's a symmetry to this notion of being jump equivalent. And maybe this is another good thing to check. Actually, let me go this way. Yeah. Check symmetry of jump equivalence. In other words, if there are jumps taking delta prime to delta, then there ought to be jumps taking delta back to delta prime. So you can think about that. And so here I'm just saying you can go one direction or the other. One thing I did mention, I'm surprised none of you brought this up. Maybe it's because this drawing ended up being so awful. But the band B is lying in the boundary sphere. I didn't say that.
You implicitly bubbled it up.
Yeah, so here I didn't bubble up, but it's actually, it's important that it lies in the sphere. Because I didn't mention anything about framing, so that is actually, that's pretty important. And then what I did then when I formed the new guy is then I bubbled it so that it would become properly embedded. Okay, so I just sort of perturb after I do this banding, the new guy, delta I prime, actually sort of intersects the boundary in the interior of the band. But then it just, this sort of thing happens a lot. Because you want things to be in general position, but often the easiest way to describe them is when it's not in general position. So you sort of do something in a not general way and then you perturb it. Awesome. Okay. Okay, so we've got 5 minutes left, which is perfect because I wanted to give you guys a chance to prove this proposition before I go. I'm pretty sure that's what I'll do next time. Unless maybe you need a little bit longer to try it. I don't know. But I think you can do this. So this is going to involve. We've already talked about an innermost curve argument, right? So this is more innermost curve stuff going on, and it also involves now an outermost arc. So this is what you would call an innermost curve, outermost arc argument. We only needed curves when we were intersecting closed surfaces in three manifolds and trying to play around with the intersections. But now that we have these two systems, they are surfaces with boundary in a three manifold. And so when they intersect, it won't just be in closed curves. So for example, if I have let's see, system 1 here, and maybe the orange guy has yellow disks, and then I have system 2 over here. The green guy has red disks. I guess the arcs are the same thing. Yeah. So I basically am embedding each of these membrane systems into the same 3-ball so that their boundaries agree. But then what happens is, the red guys will crash through, and there could be arcs of intersection and curves of intersection. And then similar over here, the yellow guys show up. Should probably have a similar number of.
Well, can those arcs go to the tangle itself?
Yeah, like I've drawn.
Yeah. Because they flip around each other.
Yeah, good message. Yeah, take a bridge disk, and then you'll put your finger here and spiral it. So you need to clean up these intersections. Okay, and you can do so, with these kind of cut and move arguments. But somewhere along the lines, you're not just going to be able to isotope the two membrane systems together. What you're going to have to do is somewhere along the line, you're going to have to do some jumps of this sort. So I think that's a fun thing for you to try to do on your own. And then maybe today, Wednesday or Friday, we'll do it in class. I also have it in the notes that I shared with you guys. So You could look there if you want, but I think it's probably worthwhile to try it first. Alright. If this were a 45-minute class, my lectures would be like perfect every time. Just 5 minutes off. All right, so let's see. Does anyone want to ask a question?
I'll ask a question. Number
Please.
4 over there.
Yeah.
It sort of sounds like it's equivalent to each strand being unknotted. Forget about the other ones. But I know from experience that that's not equivalent to being trivial, right? So that's, you're like.
It's not quite enough for the strand to be, well, it depends on what you mean by unknotted, when you call a
When
strand
you
unknotted.
delete the other ones, just as one symbol.
Right, that is not enough, you're right.
And so that's, yeah, it just.
This is stronger, this is somehow saying it's unknotted in the complement of the other ones. Which, as it says, oh, I see, you're talking about this one, but yeah,
Well,
this one, or even these are.
since you say you know from experience, it's from what I always forget. What's the example where it's not? Each
I
one
was
is
asked Jeff to try.
Oh, really? No pressure. So what do you want an
I
example?
want an example where each strand by itself is trivial,
Oh, yeah.
but the collection of them is not trivial.
I should make you do it.
Yeah.
Let's see, hopefully this is the right example. This equator always gets in the way, doesn't it?
I see.
So each of those strands is clearly trivial if you delete the other ones. But neither of them bounds a membrane. Yeah. Oh, I guess, is it true? Okay, careful. Another thing that's true, maybe I'll just say this, is that the group of a trivial tangle. What is the group of the trivial tangle exterior? Okay. 7 seconds.
Component.
B, always B.
Z,
Free. It's gonna be free.
Abelian or?
oh,
By group, he means fundamental group.
Yeah, I don't know. But yeah, I mean, you're basically right. I mean, so here's a good way to think about it. We know the trivial tangle is diffeomorphic to this thing. What's the group of this thing? Well, it's just the group of a disk with a few points removed cross I, and the group of a disk with B points removed is a free group on B letters. So the group of a trivial tangle is free. That's not an equivalent. That's not an equivalent thing. So there are things called, I think they're called free tangles, which are tangles that have the free group. So maybe try to come up with a tangle whose group is free, but that's not a trivial tangle. Okay, we'll stop there today. Oh, I just want to try it. It's like impulse. Yeah, this is fun.